All right, so this is the Chapter 15 first presentation, Part 1 of Chapter 15. So this continues on for Module 3 after Chapter 14. So key points for Chapter 15, we've got these reaction types, neutralization. This goes back to Chapter 14, acids and bases. We'll be doing a little more of that in this chapter, but we'll also be moving on to a few other newer topics like dissolution, precipitation. Common ion effect, we've hit on that a little bit before, but we'll see it in a little more stark relief here. Buffers, again, that connects back to our acids and base titrations as well. Solubility, again, dissolution, precipitation. These are ideas that will be new to this chapter. We won't be covering the qualitative analysis nor the fluoride ion material for test 3. Neutralization reaction. So we touched on this a little bit in Chapter 14, but this is a reaction between an acid and a base that results in a complete reaction with the added base or acid, so like an equimolar addition. Common ion effect, the shift in equilibrium upon adding a substance that provides more of an ion already present. So this is related to Le Chatelier's principle from Chapter 13. It can affect all types of equilibria, including acid-base reactions and solubilities. And this is what's going to actually change up our ice charts a little bit. We were talking in Chapter 14 about how some of these ice charts were seeming a little boring because we kind of got the same shape each time. Well, common ion effect will give us something else to put in some of those other positions where we were just seeing X before. So it'll get a little more complicated there. Solubility products constant. So this is the equilibrium constant for a dissolution or dissolving reaction or process. Now I say that because sometimes a dissolving that doesn't produce something insoluble or something like that is not always, strictly speaking, considered a reaction. Think back to your early chem where you had to write like the net ionic equation or something like that. So sometimes people don't consider that to be a reaction, but we can still write an equilibrium constant for it anyway. So we're going to think of it like it is a reaction regardless in this course. Ion product, so this is the reaction quotient for the dissolving. So meaning, thinking back again to Chapter 13, this reaction quotient is like the fake K, the number where we don't know whether or not it's really at equilibrium. That's our ion product. And they give it a special name when it's in a dissolution reaction, but it's the same basic concept as Q from earlier. Formation constant for the formation of a coordination complex. We talked a little bit about those when we talked about the aluminum ions and waters associating with them. That's an example of something like this, and sometimes they'll write this as a KF. Just like we see KSP, KA, KB, KC, KP. Got a whole alphabet soup of Ks now at this point, right? So buffers are solutions that contain a weak acid and weak base and its conjugate, and they can resist drastic changes in pH. We'll talk about how to do calculations and such with them. Acid-base titration, the process by which a solution containing a known concentration of known base or acid is slowly added, and we can use this to identify how much or what the identity is of an unknown acid or base. So if we know the amount that we're adding to, we can do the calculations to get like a Ka for a weak acid or a Kb for a weak base and use that to identify it. If we know that going in, we can calculate the amount, an unknown amount of something. Titration can be used to identify an unknown acid or base or to quantify the amount of a known acid or base present. That's really the theory going on here. Typically it's the latter, it's quantifying, but you could in theory do the other one as well. pH titration curve, a plot of the pH of a solution is a function of the volume of some added titrant, which is this added solution where we're changing things with. We'll see this in a little more examples. And the equivalence point is where we have stoichiometrically equivalent amounts. That's that equimolar quantity. We may have multiple points where this happens if we have polyprotic acids or polyhydroxyl bases. And the endpoint is where an indicator changes color. It's not necessarily the same as the equivalence point. This is more of like a titration term of art thing. You'll see this commonly asked in questions. Equivalence point and endpoint are not the same. You would want to pick an indicator whose color change endpoint is near the equivalence point. Again, typically today, people just use pH meters. But you should know these terms anyway. Okay, so for neutralization reaction, strong acid and strong base, what do we have going on here? So we could look at this as the reaction between some strong acid and strong base. Instead of looking at it like they both react with water and then we like combine them, we can look at this more directly, right? And since these are both strong, these will completely dissociate, and this will go to completion, right? And we know that this sodium chloride is a neutral salt. So we work through this basic theory. We know that this reaction essentially goes to completion and that the net result is essentially neutral, right? So what if we have a weak acid and a strong base? Now we've looked at this before, and we've said that, you know, the leftover salt here should be basic because we're going to have this leftover acetate ion that's going to form some basicness that's going on here. They're adding these together, and they're able to combine these two constants to get this net reaction at the neutralization point. And if we look back previously, we could see that this neutralization is just a very, very strong reaction because essentially it's the inverse of the Kw. These are combining together to form water, and that's essentially the inverse of the Kw. But if we look at this example, we see that this still has some equilibrium driving it forward, but it's not as high as the previous example. So this neutralization has a tendency to move forward. It has a very large K value, which is basically just the sum of these two steps, right? We've just summed together Ka and the conversion of that leftover acid base to water, and then we have this leftover, you know, basic product here. You know, if we have leftover acid, then we might have something like this left over. It depends on how we would have to cancel everything out. So the resulting Kn, which is for the neutralization of a 1.8 by 10 to the minus 9, means this neutralization reaction proceeds essentially to completion. Most neutralizations will go essentially to completion with just their leftover salt or whatever is left over at the end. If they have any leftover protons or hydroxide ions, then those will control the pH of the system, right? And they talk about here that the pH would be greater than 7 because of the weak base. So all of the stuff that we learned before is true. We're just looking at the strength of this neutralization process in and of itself, right? So once again here we have the reaction, weak acid, weak base. We look at we obtain the equilibrium constant for the neutralization by multiplying the reaction constants together. We essentially treat the strong acid like it is, and then we end up with this inverse reaction. It turns out that these happen to be the same value, but they mention this is by coincidence because they happen to have very similar Ka and Kb values. Acetic acid and ammonia happen to have similar values for their Ka and Kbs respectively. This is kind of weirdly coincidental, but it just happens to be true. That's how this number ends up being here. So the Kb for ammonia is about the same as the Ka for acetic acid. They're roughly equal in strength in opposite directions. It's just kind of a fun fact. So it turns out that this inverse tendency here that we get from dividing these by the Kw tells us that these neutralization reactions generally go to completion, and that's kind of the effect of all this. Now, when we have weak systems, we have a much lower K value because now we're combining two Ka values together. We weren't able to ignore the one and just kind of treat it like it was just the water, which is what we did before. Now we actually have to combine all these different steps together. So this is sort of what we were talking about if we had like a neutral salt, kind of what we might have to do by combining all these different steps together to cancel everything out to get an overall reaction. We'd have to do something like that in that instance here. Here, though, we're also including the Kw because we want to see what the tendency of the system is to be driven to completion, which involves the reaction of H3O plus and OH minus forming water, which is actually a really, really powerfully strong reaction. It progresses forward really, really well because remember that the inverse reaction is the Kw and it has a very negative exponent. So that tendency tends to pull most acid-base reactions to completion. And that's what we're really seeing here. So although this is lower, the system still proceeds toward completion, but it doesn't necessarily go all the way toward completion in this instance. It's just not as big of a number in these instances, but it still highly favors the products. Weak acid, weak base neutralizations have less tendency to proceed to completion than neutralizations involving strong acids and strong bases. Those neutralizations are assumed to go essentially to completion. And as we saw, they had very high values for their Kn value. But now, for these reactions, we see a much lesser tendency, like 5 orders of magnitude-ish. But it still does proceed that way. Here they have of the neutralization of HCl with aqueous ammonia has a value of Kn less than 1, which means the reaction proceeds less than halfway to completion. Again, this now means since it's less than 1, it actually favors the other direction. So most acid-base neutralizations, if you have a weak acid or weak base with a strong one, those proceed to completion. But most weak acid, weak base ones still do, but not very well. Now, the worse the acid and the base get, the less this has a tendency to go to completion. And that intuitively makes sense overall. So if we have something inert, obviously we're not going to see any real reaction here. So here we're breaking these down into steps again, right? We've got this acid, we've got this base, and we got the water as well. And they break this process down into steps. But in this case, we're actually going to include this, this process here. Because they have 2 acids and 2 bases, there are 4 possible transfer reactions. They talk about how we've got a reaction of this acid with this base. Okay, and since this is just the same reaction in both directions, the K would be 1. They cancel each other out. And then they have this down in here where you have this extra going on, this extra reaction. This assumes this kind of takes care of it if you have more than one or the other. First, these reactions has a larger equilibrium constant. We can't consider it because everything's identical. Okay, not a problem. So we have this overall reaction where we're donating a proton. And then we end up building a setup here where we actually had the starting amount. See, in this instance, we actually had a starting amount of acetate, unlike previously. So as you can see, our setup in the ice chart is going to be significantly different. And once again, we can make an assumption where if we can make the assumption that the x in the denominator is not significant, we can also make that assumption in the numerator and reduce this down. And then again, they'll both cancel out because they had the same concentration, but that may not always be the case. And then you could solve this for x in a similar way and then obtain the pH that way. So these types of problems where you actually have something present on both sides, you're not going to be able to use the Chazy equation for problems like this. But like I say, in general, if you can make the assumption that subtracting works, you can also make the assumption that adding works. And that may assist you. Even if this is like a 2x or something like that, you may still be able to make that assumption, keeping all of this in mind. It's interesting, they say, to compare the H3O plus concentration of a 0.1 molar acetic acid sodium acetate solution with the H3O plus of a 0.1 molar of pure acetic acid. The principal reaction is the same, but in 0.1 molar acetic acid, all the acetate ions come from the dissociation. So in this case, they're going to work it out. But they show us here with the color change that if we don't have any acetate present to start with, we get a pH here. Or actually, no, this is the one where they have them both present, sorry. When they're both present, we get this pH here, which is, of course, higher than if we only have the acid present to start with. This makes sense. If you had some base in there and then you added the acid on top of it, you'd expect that the overall pH would be higher. It would be less acidic than in the case where you only have the acid present. So they say that this methyl orange is pink when it's more acidic and it's yellow when it's more basic. So you can see that that's happening here. I mean, 4 is still acidic, but it's less acidic than 2. So that's what I'm comparing here. So the presence of having some of this extra base around when you went to start, it changed things. And that's what's going to be really important. This is principally how we're going to get into this common ion effect and ultimately lead into buffers. So the common ion effect means that if I start with something in the solution, or if I get something from another equilibrium that is present in a next equilibrium, I have to carry that through, and it's going to decrease the tendency of subsequent equilibria to progress in the direction where this thing is. It's an application of Le Chatelier's principle. Essentially, from an ice chart perspective, it means having things in those other variables to start. When in the initial, I didn't just have one, the acid or the base to start. I actually had some existing acidity or some existing one of the other ions present. And so that had the effect of, and in these systems, it tends to push it toward the left and cause the solution to become less acidic upon addition, let's say, of an acid to an existingly, to a solution in which the conjugate base or acid is already present. These things tend to push it to the left. Common ion effect is another example of Le Chatelier's principle where stress and equilibrium, so the position of the Ka doesn't change, it's just that we already had a product already present, so that tends to push equilibrium to the other side. So let's look at an example. I think this will kind of help us with this. So they say here that we have this solution, right? They want the percent dissociation in a solution that's 0.15 molar in ammonia and 0.45 molar in ammonium chloride. Now we know the chloride ion doesn't do anything, but the ammonium does something. So we would have to set up an equilibrium setup to do this. They say for comparison, the pH of this solution that contains none of this is 11.21 and the percent dissociation is 1.1. Okay. Now later on we're going to learn an equation that's going to make doing problems like this really quick. But before we do that, we have to look at the basic principle of what's going on. So now we can see an ice chart where we actually have values plugged into everything. We're going to assume that this hydroxide starting is 0. Again, it would be about 1 by 10 to the minus 7 if we did, but it's a lot smaller than everything else. So we can set this up, and again, if we have plus x and minus x, we're going to assume they're not there. We can't use our cheesy equation to work this one out, though, because we have a different arrangement. We can't just take a square root anymore. So we have to actually work this all the way out. So when we work this all the way out, we end up with a hydroxide ion concentration of 6.0 by 10 to the minus 6. And then we do a little adjustment to check our assumption here. And then we follow up by calculating the pH. You could get the pOH too, like I talked about, and the percent dissociation, which is very small. So originally, if we didn't have this NH4 plus present, the pH would be 11.21. But now it's only 8.77 because we started with the addition of the conjugate acid already being present. So this is the example of the common ion effect, where by having some ammonium already present, we're able to affect the dissociation of ammonia. Now, you can see there might be some applications to this. What if I had something I didn't want to dissolve? What if I wanted to have something present that kept something else from adding, subtracting, or changing? That's kind of the thought process that goes behind the buffer, but it also can go behind protecting something from dissolving by putting it in a solution that contains a bunch of the ions already so it doesn't dissolve. You could say, well, what if I had some kind of artifact I'm going to claim? It's made of a mineral that contains fluoride ions. So if I put it in distilled water, then it will dissolve into the water and release these fluoride ions, let's say. But if I put it in water that already contains fluoride ions, the already present fluoride ions will limit the release of fluoride ions and it'll keep it a solid. So this is kind of the thought process behind common ion effect. We could use a cheese equation here to get a ballpark, to get this 11.21, and we know that it would need to be less basic than that because of the presence of the conjugate acid, but we wouldn't be able to actually calculate it any further. So let's talk about buffers. So to make a buffer, you've got to have a system of a weak acid and its conjugate base. And to keep everything simple, you typically want to use the weak acid and its conjugate base. In theory, you could use another base, preferably one that had similar properties to the weak acid, like a similar value. Otherwise, you're going to run into some problems. But usually you want to use the weak acid and its conjugate because that will produce something that's easier to understand and predict the behavior of, right? So if you have these buffer solutions where you have a large amount of a weak acid and its conjugate base present at the same time, then the addition of a small amount of H plus or OH minus will change the pH, but not by very much because it will immediately be consumed by one of the weak acid equilibria, and then it will disappear from the system. So think about it like this. If a small amount of H3O plus is added to this buffer, the pH decreases because the base component of the buffer neutralizes the added H3O plus. So you can't do this with a strong acid and its conjugate because they don't have any equilibrium. This only works with a weak acid or weak base and its conjugate. They give us these examples here. So the reason this works, and they set up the math to kind of explain why this works, is that if we build an equation that explains this, right, we see that we can cancel out these to initial concentrations, and we can set these up and we can make the simplification that we've seen in some of the previous problems. If we solve this equilibrium expression, okay, for H3O plus, we'll get this, okay? And then we plug in what we have. We'll end up with something like this, which will be Ka and the two concentrations. And if they're the same, then they'll cancel out, and the H3O plus concentration will be the Ka. Or another way to say that is that the pH is equal to the pKa. And that's typically where buffering capacity of a system is the best. So if you pick a weak acid conjugate base combo, you'll get the best buffering capacity when they have the same, you put in the same number for both, and you are close to your pKa. Your pH is close to your pKa. So that's like the ideal buffer, where the capacity of shifting, you have the greatest capacity to absorb acid per unit of acid and base present in the solution. So that leads to the ideal buffer, right? So here they show what happens if I do some kind of change, right? I do some kind of change, and then I plug these numbers back in and I do the math again. I see that the change had to be applied to the existing acid or base, because I'm just throwing in like a bunch of hydroxide. I'm just throwing in like a strong base or something like that. But the adjustment that occurred is relatively small, as long as it's not too much above the order of magnitude of the present starting amount, okay, right? Because if I just overwhelm these, then this will all break. They call this breaking the buffer. If you just put in so much acid or base that it just essentially overwhelms everything here, then that won't be there. Now, the reason this hydroxide disappears is because it went into this acid. It reacted with the acid and turned it into base. So the reason this kind of conjugate thing works is that if I add acid or base, I'm just converting back and forth between the two conjugates, the ones that are in a conjugate relationship with each other. And as long as that change between the two of them doesn't substantially change the ratio of one to the other, then this will work. So 0.1 to 0.1 is about the same as 0.09 to 0.11. So the pH only changes a little bit off from that original pKa value that we looked at earlier. So that's what's helping us. That's how the buffer is working. It's that these two don't change very much. If they change dramatically, then the buffer is broken. But you can see how we can absorb small additions because this ratio stays about the same. Okay, so that's the basic theory of a buffer. Like, that's the theory of how a buffer works. You could add H3O plus or OH minus to the buffered solution, and it stays roughly the same pH. These are really useful in building systems that can stay about at the same pH. Biological systems need to use buffers because they can't withstand large changes in the pH of the liquids that flow through them. They'll kill cells, so they build buffer systems that can insulate them against big changes. So here they show the addition of H3O plus. The same basic theory happens, and we see only a small change in the pH from the initial starting value. Like I say, the capacity of a buffer has to do with how close you are to the pKa with your set pH, but also the relative ratio of the strong acid to the weak acid to the weak base. You want to have those be about 1-to-1, and you want to have a lot of them. You know, the more you have of them, the more capacity it has. They talk about buffering capacity, a measure of the amount of acid or base that the solution can absorb without significant change. Buffer capacity is also a measure of how little the pH changes with the addition of a given amount. Okay, so it depends on how many moles of the weak acid or weak base is present, and it also depends on how close you are to those two things being equal, so your pH is close to the pKa. Those are all kind of ways of saying the same thing. So here you have HCl. You add with only a few drops of sodium hydroxide, we can change the pH. But in a buffered solution, you have to add a lot more, and it doesn't really change the pH very much. So this is an interesting advantage that these weak acid, weak base systems have over a strong acid, strong base system. So this is the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation is a quick and dirty way to get buffer pHs. So you have to have a buffer system in order for this equation to work. It's based on the same assumptions that the Cheesy equation makes. In fact, I made the Cheesy equation by rearranging the Henderson-Hasselbalch equation in the scenario where the pH is there's not any of the conjugate present, and reworking that ends up getting that equation. It's a similar concept idea. So with the Henderson-Hasselbalch equation, we can get the pH by taking the pKa of some acid in the system and then arranging it this way. It is possible to also write the Henderson-Hasselbalch equation in terms of pOH, pKb, and then you flip the base and the acid. So it's conjugate over its thing, the way that it's arranged here. So if you wanted to do it the other way, you could do pOH, pKb plus log, then it'd be the acid over the base if you did it as the basic version. But that also works. The Henderson-Hasselbalch equation, though, is usually written this way because we typically like to see pHs and pOHs. And this text in particular seems to be a little biased against having a lot of pOH. They don't seem to do a lot of those in their problems, but it gives you an idea. So you can use this same basic approach to work. And this makes all the same assumptions as the Cheesy equation and as the 5% assumptions and everything else. So all those have to all be true in order to use the Henderson-Hasselbalch equation. But it works really well, and it'll work for any system where the base and the conjugate base and the acid are present at the same time. So this is a good way to get around the fact that we had to set up all this ice charting and doing all this equilibrium work for these systems where we had conjugate present. Now we don't have to do that. We're able to do this Henderson-Hasselbalch and get a rough estimate for our buffer pH without having to do all that extra addition. And we'll be able to use this in problems that don't even explicitly say they're buffers, but just give us certain scenarios, right? So if we work all this out, we're able to figure out that by starting with a certain amount, okay, when the base of our acid is 1, then the log is 0, so the pH equals the pKa. But if that's not the case, then we'll need to make an adjustment. So they say here, one of the molecules or proteins remain at the pH of the solution is 2 pH units greater, so you'd be able to plug that in and then work backward to calculate the value of this log. So you could tell here that there's a 99% dissociation going on here with this. And this gives us the following relationship. So we're able to use this to connect percent dissociation with the Henderson-Hasselbalch equation. So the idea is even systems that aren't explicitly buffers, like this example of this protein that they were looking at that establishes an equilibrium with its conjugate base, we're able to still use that, okay, because we know that the pH of a solution is 2 pH units greater than the pKa. We're able to use this to calculate how much it dissociates, and you still get a base-acid ratio that exists. You don't need to memorize all of these, but I think it's an interesting relationship between percent dissociation and the Henderson-Hasselbalch equation, and the fact that we can use it even then. They say here, as a rule of thumb, the pKa of the weak acid component of a buffer should be within 1 plus or minus 1 pH unit of the desired pH. The buffer gets worse the further we move away because we need to adjust the ratio of base to acid, and we lose buffering capacity when those two aren't close to 1. So that's something to keep in mind. The pH of a buffer does not depend on its volume, and it depends on the setup, not the volume. And it also doesn't depend on the amounts that are actually in here. It just depends on the ratio. So let's use the Henderson-Hasselbalch equation to calculate the pH. So we'll start with the Henderson-Hasselbalch equation and just plug those things in. So they say here, pH of a buffer solution that is these. So I need to get the pKa, and we can do it in the form of the acid because that's the typical way that we do it. Doesn't really matter which one. So we can go obtain the pKa, which is what they do first. They get the pKb for the ammonia, and then they convert it. But I would just stick with the, if you could look up the NH4 one. Otherwise, you can convert them with the Kw like they do and obtain the pKa for the acid component. Put that in here. Then the ratio of the two. Those are just the two numbers given to us in the problem. And here it's the base over the acid thing, conjugate over the thing. Remember this order. Make sure you don't get these backward because you'll get crazy numbers if you do. And then solving this will end up with the pH. Now that makes sense that this is, because it looks like here, this is a little bit, this is a little bit basic. Now that kind of makes sense because if you look up here at the KB, this is a much better base than this is an acid. Even though there's less base than there is acid, there's like 5 orders of magnitude difference between those Kas and Kbs. So keep that in mind, that may affect things as well. How would I prepare one that has a pH of 9? So that would again mean going back to the Henderson-Hasselbalch equation, solving it for the difference, and then using this to come up with a ratio. So it must contain 0.5 moles of NH3 for every 1 mole of NH4Cl. Volume is not critical. That is the only requirement. So essentially the two concentrations have to be in that ratio, but it otherwise doesn't matter. You could make it as long as that ratio is true. So let's take a look here at pH titration curves. So for pH titration curves, these are built by taking pH readings. If we were going through this class in a seated version, I'd have a lab where you would do a titration, at least in the Chem 151 kind of level version of this course component. We would actually build a curve like this from our points, and we could do this with a pH meter in the slow addition. You may have already done something like that at this point in this course, but maybe not, depending if you just took everything online. So we add some titrant, which here is sodium hydroxide. Usually it's a strong acid or strong base, and we titrate the thing, which is usually a weak acid or a weak base, to go along with whatever strong one is here. So we're titrating some weak acid with a strong base. Now we're seeing here the equivalence point is 7, so that actually tells us that this is a strong acid and not a weak acid, because the equivalence point for a strong acid, strong base system is 7, but otherwise the equivalence point is shifted, and if it was a weak acid, it would be a higher pH, it would be basic. The position of equilibrium, equivalence here would be basic, and if it was a weak base with a strong acid, then the position would be somewhat acidic. Keeping all those things in mind, this is a curve that would help us figure this out. We could figure out that the pH at half the equivalence point, there's a formula that tells us the pH at half the equivalence point is the pKa. That actually comes from the Henderson-Hasselbalch equation, because we're able to figure out that at this half equivalence point, that's where you have equal amounts of both. You haven't canceled them out yet. So that's another realization that you can do that using the Henderson-Hasselbalch equation. We talk here a little bit about molarity. This is more of a reminder at this point. You should kind of know what molarity is. This is how we've been measuring concentration all up to this point. The equivalence point is when everything is canceled out. So, like I said, this half equivalence point is where half of each one is present, and that would be the point where the system would make a buffer where the concentrations would both cancel out. So the pH could equal the pKa. Titration is a procedure for determining the concentration of a solution by allowing a carefully measured volume to react with a standard solution of another substance whose concentration is known. All right, and that is the end of this presentation. In the next ones, we'll take a little more look at pH and buffer systems and a little more interesting things there, and take a look at the dissolution processes as well. All right, thank you so much for your attention, and I will see you all in the next one.